Hi, my name is Stanley Samuel and I'm a PhD student at the Department of Computer Science and Automation, Indian Institute of Science in India. I will be presenting our tool GenSys, which is a scalable fixed point engine for maximal controller synthesis over infinite state spaces. This is joint work with Professor Deepak D'Souza and Professor Raghavan Kumandur. Automated synthesis of controllers, also known as reactive synthesis, is practically motivated and has various applications in the realm of finite state and infinite state systems. Examples of finite state reactive synthesis include synthesis of bus arbiters and cache coherence protocols, whereas examples for infinite state systems include the synthesis of robot controllers for obstacle avoidance and for the synthesis of intelligent strategies for the minimum backlog problem in wireless sensor networks, to name a few. In this talk, we will focus on the synthesis of controllers for infinite state systems under a given temporal specification. More specifically, we focus on an abstraction of the minimum backlog problem in wireless sensor networks, which is also known as the Cinderella-Stepmother game. Before getting into the details of the game, we first need to understand what a two-player game is, which is what I explain next. While modeling such systems, we can view it as a game between two non-cooperating players, the controller and the environment. The game has an infinite state space, which we denote by S. Both players take turns in changing the state of the game. For this talk, we consider safety as the winning condition and G of S as the predicate describing the set of safe states. The allowable moves of each player denoted by the transition predicates con SS dash and NSS dash respectively, where each player transitions the game state from S to S dash. The controller is the protagonist player for whom we wish to find the strategy such that it can win against any series of moves by the other player, which is the environment. A play of the game is an infinite sequence of steps where each step consists of a move by each player. In this case, starting from state S, the controller plays first, followed by the environment, where state updates are denoted by primed variables or dashed variables. A play is winning for the controller, that is, does not reach an unsafe state if each state in the play satisfies the predicate G. The aim of synthesis is to find a winning region and a winning strategy for the controller if there exists. A winning region consists of a set of states from which the controller will win if it follows its strategy. The strategy tells the controller which move to play from any given state in the winning region. The state space, safe region, controller move, and the environment move denote the game specification given as input to GenSys. We will discuss this with a concrete example. A classic example of a game with infinite states is that of Cinderella-Stepmother and is considered to be a challenging problem for automated synthesis. The two players of the game are Cinderella, who is the controller, and the stepmother, who is the environment. In this game, the state space consists of 5 buckets arranged in a circle with a fixed capacity of C units each. In this case, the 5 buckets are B1 to B5 respectively. In each step, Cinderella is allowed to empty any 2 adjacent buckets, whereas stepmother can arbitrarily distribute 1 unit of water across each of the 5 buckets. Cinderella wins if throughout the play none of the buckets overflow, which is captured by G. Otherwise, stepmother wins. Cinderella has a winning strategy when C is greater than or equal to 2, and doesn't, that is, stepmother wins, when C is greater than 0 and strictly less than 2. The challenging range for automated synthesis has been conjectured to be between 1.5 and 2, and we show that GenSys can easily scale in this range, when no other previous tool could. GenSys is a prototype tool written in Python and takes as input a game specification which essentially contains Python definitions describing the moves of the controller, environment, and the safe region. A condensed example of the Cinderella game specification is shown. Based on this specification, GenSys formulates the game and employs a lean fixed point algorithm to compute the winning region and strategy if it exists. It is possible that the procedure may not terminate. More details are explained in the accompanied paper. This table shows the running times for Cinderella game for various values of bucket size C, ranging from 3 to 1.4. R indicates that the game is realizable for Cinderella, whereas U indicates that the game is unrealizable for Cinderella. We compare against 3 state-of-the-art tools, SimSynth, ConSynth, and JSynthBG. We showed an example where GenSys takes around 30 iterations to solve the game. We show here that GenSys is capable enough to solve for 69 iterations and takes only 31 seconds to solve. You can see that no other tool could beat this. Also, we see that GenSys takes significantly lesser time than all the other tools in this domain. We have presented the prototype implementation of our tool GenSys. We discussed the design of the tool using a motivating example and demonstrated scalability of strategy synthesis and readability of synthesized strategies. Thus, we show an elegant solution that works well in practice. More information about our approach, running the tool, and reproducing the results can be found on GitHub.